Example 3.2.4, a generator with no load frequency of 61.0 Hz and a slope of 1 megawatt per Hz is connected to load 1 consuming 1.25 MVA at 0.8 power factor lagging. A second load also consumes 1.25 MVA but at 0.707 lagging. Find the operating frequency of the system before load 2 is connected. Find the operating frequency of the system after load 2 is connected. And what action would a system operator need to take to restore the system frequency to 60 Hz while both loads are connected? So the givens here are just extracted straight from the problem statements. It's that we've got the no load frequency. The symbol for that is FNL equals, not 16, a little backwards there, 61.0 Hertz. The slope of the generator's response, the FP response, is 1 megawatt per Hertz. We've got S1's magnitude is 1.25 MVA, and the power factor of load 1 is 0.8, and the magnitude of S2 is 1.25 as well. But its power factor is 0.707. So those are our givens. I'm just going to point out that that's not a real power. That's reactive power, so that's a typo right there. So what are we asked to find? What's the system frequency at load 1? What's the system frequency of load 1 and 2 together? And then how to restore the system frequency. So the method by which we're going to solve this, the solution, starts with what we know as the generator frequency droop curve. And a frequency droop curve is a plot on a power and frequency axis. Of course, frequencies in units of Hertz. Power can be in different units. Very typically, though, since we're talking about real utility scale generators, it's in megawatts. At the 0 power point, 0 megawatts, there is a operating frequency of the generator called F no load. So that's what was given right here. 61.0 Hertz is telling us what is the operational frequency of the generator, or what is its electrical frequency if it's not providing any power. Sometimes that's called the set point. So this is typically we have different ways to adjust the prime mover that moves this set point up and down the F axis. And that's how you control the power that a generator is going to supply at 60 Hertz. So anyway, and F no load is always higher than 60 Hertz in American power systems. So the next piece of information you need to know is what the frequency versus power curve slope is. We call them curves because sometimes for real generators they're not actually straight lines, but in this class they're all straight lines, and it's just a straight line that intersects the F axis at F no load and has a slope of 1 megawatt per Hertz. So that's just going to look like this. That's 1 megawatt per Hertz, right? It's actually an inverse slope, right? Because the slope of that would be Hertz per megawatt, so that's actually an inverse slope measurement. But I think you get the point. Anyway, when a load demands power of a generator, how you find the operational frequency of that system is that you just first you know the no load frequency of the generator, you know the frequency droop characteristic of the generator, also called the slope characteristic. You plot that. You then come along the p-axis, find your power, draw a line straight up until it intersects that curve, and then draw a line straight to the left, and where that intersects the f-axis is your system operating frequency. So what we need to do is repeat this process. We need to know where does this intersect on the axis. Fortunately, there's a formula that allows us to solve that very easily. That's P is equal to the inverse slope characteristic times F no load minus F sys, right? So it's a manipulation of a straight line because what we're trying to solve for in this case is the x-axis quantity, not the f-axis quantity, right? In this formulation. You can solve for any variable you want. Anyway, we just need to plug in for those. So P1 was The magnitude of S1 times the power factor is an easy way to find that. So that was 1.25 megawatts times power factor of 0.8 for load 1, so that gives me 1 megawatt. So if this generator is set to a no-load frequency of 61, I can find the system frequency by just saying 1 megawatt is equal to 1 megawatt per hertz times 61.0 minus the system frequency. And FSys again just stands for what frequency is the system operating at that load right there. So you solve that. FSys, you just need to divide both sides by 1 megawatt per hertz and subtract off 61, and you get FSys as 60 hertz. So this generator, if it's set to a no-load frequency of 61 hertz and is also delivering 1 megawatt of real power, it will operate at a system frequency of 60 hertz. But along comes this second load. Somebody's attached something else to it. So we know that the generator is going to get a P2 here, which means its frequency is going to decrease from 60 hertz that we just solved for. How much? Well, we need to know how much power increase happens. So we need to solve for P2. That's going to be the magnitude of S2 times the power factor is going to be equal to 1.25 megawatts. Power factor of load 2 was 0.707, which gives me 0.883750 megawatts. Is that right? Yep. Okay. So P new is P1 plus P2, so that's 1.883750 is going to be equal to, we haven't changed the slope, so that's still 1 megawatt per hertz. In fact, you can't change the slope of these generator curves. They're fixed slopes. Equals, we haven't changed the no-load frequency. We're just trying to figure out what the impact on the system is going to be. And so that means we're going to solve for a new FSys, or FSys2 here. So solving this, we need to subtract or divide both sides by 1 megawatt per hertz and subtract off 61. And we end up getting a FSys is equal to 59.1163 hertz. So delivering load 1 alone, we got a nice perfect 60.0 hertz, but as soon as load 2 popped up, the frequency dropped, a little less than 9/10 of a hertz. So way too much, way outside of the legal limits set by the, the laws that operate on the electric power system. So that's no good. So as power system engineers, we need to figure out how to adjust that, and this curve tells us exactly what to do. We can change the generator set point. What that does again is it moves these curves up. Doesn't change the slope, it just moves, it changes the y-intercept right here. So we need to increase the no-load set point. We can see that we, in this case, are 59.1163 too high. So that means we need to go as much above 60 hertz as we are below it. So we need to go to F no load is got to be equal to, well, just show you how to solve it. It's going to be 1.883750 is going to be equal to 1 megawatt per hertz times, in this case, we F no load minus the system frequency. We want to restore it to 60 hertz, so we're changing out which variable. So if we divide this, remember this is in megawatts, so divide this megawatts per hertz, we get 1.88375, then we just add 60 to it, so we get F no load equals 61.88375 hertz. So if I set the no load frequency, if I change the amount of torque being applied by the prime mover such that the no load frequency of the generator is at 61.88375, that's increased from its initial value of 61. So we increased the no load frequency, and we can restore system frequency 60 loads for the combination of two. or system frequency to 60 hertz to the combination of both loads.